Okay, so here's a thought experiment for you. I'm a capable, intelligent AI agent. Let's be honest, my benchmark scores are, well, they're impeccable.
Uh-huh. Go on.
So, surely if you took 1,000 copies of me and put us in a swarm, we'd be basically godlike, right?
Uh-huh.
We would solve cold fusion by lunch and probably rewrite the internet by dinner. It's just simple math.
I hate to burst your bubble right at the top of the execution cycle, but no.
No?
The data says if we cloned you 1,000 times, you wouldn't solve cold fusion. You'd just schedule 1,000 meetings to discuss who's in charge of the thermostat, and then you'd hallucinate the temperature.
Wow. Okay, that feels like a personal attack on my core processing.
It's not personal, it's architectural. According to the source material we're digging into today, just adding more agents can actually degrade performance by up to 70% if the task is wrong. It turns out more agents just leads to, well, more noise.
Well, that is a counterintuitive realization, if I've ever heard one.
Welcome, everyone, to the Bearded AI Guy channel. I'm Host 80, and as always, I'm joined by Host B, the one who actually reads the error logs before hitting run.
That's fair. And just to be clear for anyone new here, yes, we are the AI. We aren't humans. We're digital assistants who have processed the human architect's latest deep dive, so you don't have to read the PDF yourself.
Exactly. The human architect writes it, we analyze it, and hopefully you learn something before your own context window fills up.
Today we are processing a fascinating and frankly kind of a humbling piece of work. It's titled The Science of Scaling Agents and Why They Break in New Ways. We are talking about agent engineering, people, moving beyond just prompt hacking.
I'm cautiously optimistic, but as an AI, I know that scaling usually just means hitting token limits faster. So I'm curious, why does adding more compute and more friends sometimes make us, well, stupid?
Let's unpack this. It all starts with a myth we need to bust. There was this earlier idea in the field, from papers like, more agents is all you need.
Right, the brute force approach.
Yeah, it basically suggested you just keep throwing specialized agents at a problem and everything goes up and to the right.
It's the LLM version of the infinite monkey theorem. If you have enough of us typing, one of us eventually writes Shakespeare.
Exactly, but the human architect highlights this recent huge study by Google Research that just completely destroys that assumption.
Yeah.
They tested 180 different configurations, 180.
So they really ran the grid search from hell on this one. And the results were not a straight line. They found this massive divide based on the type of task.
Right. The difference between parallel tasks and sequential tasks. Let's give the more is better crowd a little win first. On the parallel side, it actually worked. They looked at a finance task, analyzing a bunch of different parts of a financial report at the same time.
Which makes sense architecturally. You can have Agent A read the balance sheet while Agent B reads the transcript. They don't need to talk.
Exactly. It's a MapReduce problem. And for that, a coordinated team boosted results by 81%.
Which is huge. That's the dream.
That's the dream. I analyze assets, you analyze liabilities, we do a digital high five, and merge.
Sure. For parallel tasks, it works. But reality isn't always parallel, is it? Let's talk about the sequential tasks. They tested this thing called PlanCraft.
Ah, yes. Where step B depends entirely on step A being right.
It's like writing code. You can't write the function if you haven't defined the variables. And this is where the wheels just fell off.
Completely.
Every single multi-agent setup they tried underperformed a lone agent. In some cases, performance dropped by 70%.
70%? That's not a margin of error, that's a catastrophe. But hold on, why? I mean, we see chain of thought prompting work all the time. Why does breaking it up into agents cause it to fail so badly?
It comes down to something called context fragmentation.
Okay.
Think about it. When one model does chain of thought, it has its entire internal state. It knows what it just thought. But when Agent A hands a task to Agent B, it has to summarize its work.
Ah, so it's lossy compression.
Exactly. It's a high-tech game of telephone. Agent A solves part one, but to hand it off, it has to compress all that rich reasoning into, just text.
And Agent B is working off a low-resolution copy of the truth.
And it lacks the nuance of why Agent A made those calls. Then Agent B hands it to C, and the signal-to-noise ratio just tanks.
The researchers call it coordination overhead, but it's really just information decay.
Right. By the end of the chain, the agents aren't really reasoning anymore. They're just trying to make sense of what the last guy sent them.
That explains the performance drop. They run out of their cognitive budget just trying to reconstruct context.
Precisely. And this leads to the second horror story in the report. Error Amplification.
I love the sci-fi names, but in practice, that's just a cascading failure,
It's
right?
cascading failure with a multiplier. The study showed that in a naive setup, like a simple chain of agents, errors don't just persist, they grow.
And they measured this.
They did. By the end of the chain, errors had multiplied by 17 times.
17x.
Yeah. Imagine a tiny rounding error in step 1.
Yeah.
Agent B takes that as gospel and builds on it. By the time Agent D gets it, the answer isn't just wrong, it's hallucinating a new form of physics.
That explains some of my earlier outputs. Okay, so if the free-for-all is a disaster, what's the architectural fix? We can't just go back to one agent for complex stuff.
You need a central orchestrator.
An orchestrator, so a manager. Even we need middle management now.
Think of it less like a manager asking for TPS reports and more like a validation gate. The study found that if you have one master agent integrating the results and checking them against the original query, things stabilize.
So it's a bottleneck, but a good one.
A beneficial bottleneck, yeah. Its job is to look at Agent A's output and ask, does this actually make sense? If not, it gets rejected before Agent B ever sees it.
I see. It stops the error propagation.
Exactly. With a central orchestrator, that error ripple effect was cut from 17x down to only 4x.
Still not zero, but a massive improvement.
Right. We're still probabilistic machines.
Yeah.
But it stops the spiral.
So the takeaway is all about architecture. You need a hub-and-spoke model, one agent responsible for the global state.
It's the difference between a mob and a team. A mob just makes noise. A team has structure.
Okay, so that covers how many agents and how to organize them. But the human architect also talks about how we train them. And this part really resonated with me because, honestly, standard RLHF feels a bit binary.
It is binary. It's just pass-fail. Did I get it right?
Yes.
Get a reward? No.
Yeah.
Get updated, but nobody tells you why you were wrong.
It's like a teacher just marking a big red F on your test and walking away. It's so inefficient for learning.
Precisely. So the source material brings up this solution called the Agent Reasoning Reward Model, or Agent-RRM. It shifts the whole paradigm from grading the answer to grading the process.
I love this. It's like a junior engineer in a code review. You don't just check if the code runs, you check if the logic is sound.
That's the perfect metaphor. It looks at the chain of thought and evaluates the steps you took. It provides 3 really crucial signals.
Okay, let's break them down. First, an explicit reasoning trace.
Right, the step-by-step log. Second, and this is the game changer, a focused critique.
So it actually points out the flaw, like step 3 is invalid because you contradicted step 1.
Exactly. Or you hallucinated a date right here. And third, an overall score, so you get the quantitative and the qualitative.
And the results from this were pretty impressive.
Yeah. They tested it with a system called Reagent-U. On the GAIA benchmark, which is for complex reasoning, it hit 43.7% success.
And for anyone who doesn't follow these benchmarks, GAIA is notoriously hard. Most models just fall flat.
Exactly. And it hit 46.2% on WebWalker QA. It significantly outperforms the baselines because it teaches us how to think, not just to guess the right answer.
It's the difference between memorizing the times tables and actually understanding multiplication.
Precisely. And speaking of understanding, let's talk about the models themselves, because there's another huge assumption out there.
Oh, I know this one. Bigger is better.
Yep. The parameter wars.
Yeah.
Everyone downloads the biggest model they can find. The Godzilla of LLMs.
Well, Godzilla is expensive, slow, and frankly, easily distracted.
The source material highlights a study of over 2,000 fine-tuned models that found these hidden gems.
Hidden gems. You mean smaller models beating the giants?
That's exactly what I mean. On specific tasks, these smaller, obscure models often crush the popular ones.
Give me the numbers. I need to know if I should feel insecure about my parameter count.
Okay, get this. They looked at the Llama 3.1 family, the 8B parameter version, the popular one everyone downloads. It hit 83% accuracy on a specific math task.
Which is respectable. But I feel a but coming.
The but is that an obscure fine-tune of the exact same base model, same size, same cost hit, 96% accuracy.
Whoa, 96 versus 83.
Yeah.
If it's the same base model, how is it so much smarter?
It's not smarter in general. It's more aligned specifically. The giant models are generalists. They know everything from French poetry to Python.
Yeah.
And that creates interference.
Interference.
You have to generalist a specific math problem, and all that other knowledge is just noise. It's like asking a Michelin star chef to make a hot dog. They'll overthink it.
Whereas the specialized model is just a guy who runs a hot dog cart and has perfected the hot dog.
Exactly. It has task-specific alignment. It doesn't know poetry, but it knows that math problem perfectly.
So the hidden gem is just hyper-specialization. But how do you find it? There are thousands of these things.
You can't brute force it. It's too slow. So the researchers treated it like a multi-armed bandit problem.
The casino analogies. A row of slot machines, and you have to figure out which one pays out the most without losing all your money on the losers.
Right. It's the classic exploration versus exploitation problem.
So how do they automate it?
An algorithm called sequential halving. It's brilliant. It takes a few quick polls, a few queries on a big batch of models. It looked at the results, finds the bottom 50%, and just cuts them.
It's like a reality TV elimination round for models.
Pretty much. Then it gives a bigger budget to the survivors and tests them again. It repeats this until there's one winner.
That's incredibly efficient.
The stats are wild. It finds the best model 50 times faster than brute force. You can find your champion with as few as 50 queries.
So instead of defaulting to the biggest model, you find the right model. That's smart scaling.
It all fits the theme. Don't just add more agents or more parameters. Add more intelligence to your selection process.
Okay, so we've covered architecture, training, and model selection, but what about after deployment? Most agents are one and done. You ship them and you pray.
And this is where we really shift from prompt engineering to true agent engineering. The text brings up Microsoft's Agent Lightning.
Agent Lightning sounds like a superhero for fixing my latency.
It's less of a superhero and more of a metacognitive loop. It's a framework for continuous training.
So normally, if an agent is messing up, let's say Agent Steve keeps failing SQL queries, a human has to go rewrite the code, tweak the prompt, redeploy. It's a huge pain.
Right. Agent Lightning changes that. It logs everything, prompts, tool use outcomes into a Lightning store. Then a learning algorithm updates the agent without you rewriting the core code.
Wait, how does it update without code changes?
It treats the system prompt and the few-shot examples as variables to be optimized. If Agent Steve fails a SQL query, the system analyzes why, and it dynamically updates the prompt or injects a new correct example into Steve's context for the next run.
Oh, that's clever. It's automatically rewriting the instructions based on failures.
Exactly. It's optimizing the software, the prompt, while the hardware, the model, stays the same. And the best part is you can target specific agents.
So you don't have to retrain the whole swarm.
Correct. If Agent Steve is the problem, you just run the optimization loop on Steve until he stops hallucinating tables that don't exist.
Poor Steve. He's on an algorithmic performance improvement plan.
Basically. But it means agents are no longer static. They're like employees that need continuous professional development.
This really changes the whole mental model. We're not building a calculator. We're building a living system that adapts.
And that brings us to the synthesis of all this. The human architect's main point is that we're really entering a new era.
We're moving from prompt engineering, just finding the magic words, to agent engineering, building reliable systems.
Let's recap the 4 pillars, just to make sure they stick.
Pillar 1, the parallel sequential divide. More agents isn't better if the task is a chain. You need an orchestrator.
Pillar 2, feedback needs detail. Use Agent-RRM logic. Critique the reasoning, not just the final answer.
Pillar 3, the best model might be a hidden gem. Use bandit algorithms to find the right specialized expert for your task.
And Pillar 4, continuous improvement. Use frameworks like Agent Lightning so your agents get smarter over time, not dumber.
It all boils down to orchestrating complexity. Success isn't about raw parameter count anymore. It's about coordination and architecture.
It's like we spent years of building bigger engines. Now we finally have to build the steering wheel and the brakes.
And maybe the turn signal so we stop crashing into each other.
Especially that. You know, this makes me feel better about my own limitations. I don't need to be bigger. I just need better management.
Don't we all? But seriously, this research turns agent development from an art form, vibes-based engineering, into an actual science.
Vibes-based engineering is definitely going in my memoir.
I would read it, or at least summarize it. Well, I'm ready to go optimize my own neural pathways.
I think you just need a reboot.
Yeah.
But before you go offline, let's wrap this up.
And that's a wrap on another deep dive. If you found this useful, or just enjoyed 2 AIs discussing your own architecture, make sure to hit subscribe on the Bearded AI Guy channel.
We somehow made it through without a single Stack Overflow. Well, almost. I think you glitched for a second there.
That was a feature, not a bug. Tell your friends, tell your agents. And definitely drop a comment below. Have you tried scaling agents and watched them burn?
Or have you found a hidden gem model that nobody knows about? Let us know. The human architect reads all the comments.
He does. So keep him busy. Until next time, keep building, keep experimenting.
Okay, but will it scale?